So, welcome. This is the last module in the sequence about hydration reactions. And in this one, we bring together everything we've seen in the previous modules to look at how this results in the microstructure we have in hardened cement paste. Now, what I'm going to talk about here is, of course, properly regulated cements, enough soluble calcium sulfate added. And as we saw in the last module, this means that the main aluminate reactions occurs after the silicate reaction. And it therefore means that the hydration and structure development is really dominated by the reaction of C3S or halite. Now, this is the calorimetry heat evolution curve we've seen several times before. We've talked about the mechanisms that control the reactions throughout this. First of all, the induction period controlled by the buildup of ions in solution, then acceleration and deceleration controlled by the growth of the CSH needles on the surface, and finally the slow ongoing reaction. And just to relate that to the physical properties, the setting of the cement is usually occurring at middle to beginning of the acceleration period. Now let's look at how this heat evolution curve is linked to what we see microstructurally. So if we first consider the case for the silicates, what we see at the end of the induction period is we get these first formation of CSH starting to grow on the surface of the grains. And then that CSH develops very rapidly as these needles. So by 10 hours, we see these long needles from the surface. And then the hydration goes on, and finally we end up with a microstructure like this, where we have the cement grains, which are embedded in this matrix, mainly of CSH and ettringite, which is all this stuff here, and then some calcium hydroxide, which is this stuff here. Now, if we now add in the aluminate, so we have Portland cement rather than halite, during the very early reaction of the halite, we can form some very small ettringite needles, but it's, again, I'd like to stress that it's not those very small needles that are inhibiting the reaction, it's the absorption of sulfate ions on the surface. And this absorption of sulfate ions on the aluminate suppresses the aluminate reaction so that it allows the silicates to react. So here we see the silicates reacting as before. And then when we come to this shoulder peak here, we see very clearly the second growth of ettringite. We see these long ettringite needles which are formed during that shoulder peak. And then as we go on, we may not always see it, but in this case, we've got a small hydration hump here, and this is associated with the formation of the monosulfate. Now, another aspect I want to mention is this formation of so-called Hadley grains. Now, Hadley was a student working in the 70s who noticed that sometimes you could see that you had these kind of shells which appeared empty. And in fact, we see that generally if we look at these transmission electron micrographs, we can see even from very early ages, even as early as 5 hours, we can see we get this small separation of this shell and the reacting grain. So what happens is we seem to form this layer of hydrates here, and then the anhydrous grain goes on reacting, but the products are deposited outside, probably because we have this preferential growth of the CSH needles that we discussed a few modules back. And this is just another micrograph, this time taken with backscattered electrons, where you can see just how generalized these gaps are around the anhydrous grains. Now, we don't really know exactly why these form like this, but we can say that it's very much amplified by the presence of aluminates. We get a small separation in the case of pure C3S, but it's very much more apparent when we have a Portland cement, when we have the silicates and aluminates reacting together. And here are some other pictures, again by transmission electron microscope. We can see that if we now have a very careful specimen preparation, we can see this very kind of fragile looking shell of hydrates, but in fact the space in between is not completely empty. It seems to be filled with a very dispersed, diffuse product. And another interesting aspect is that this anhydrous grain here is not reacting evenly on the surface. There's actually quite deep etching along certain crystallographic directions. So what happens to these separated shells, or these Hadley grains, over time really depends on the size of the grains. If we have very small grains, 5 microns or less, then these will very quickly react during the main hydration peak, and they'll leave this kind of shell of hydrates which persists indefinitely. If the grain's a bit bigger, so in this second case here, we have a grain maybe about 10 to 15 microns, then after the main heat evolution peak, this anhydrous material will continue to react, but it may leave a small shell hole in the middle. And finally, if we have large grains, greater than say about 15 to 20 microns, then during the later hydration, this separation between the shell and the anhydrous grain completely fills in and disappears. And we can see those in this micrograph here. If you look carefully at this micrograph, you can see many little hollow shells which were small grains which completely reacted. So we've got this one here, for example. We've got one down here which is slightly larger, and therefore we've got a slightly thicker shell. We've got another one here, and the more you look, you can really see that these little hollow shells are everywhere. But for the larger grains, notably this one in the middle here, this separation has completely filled in, and we get this thick rim of inner product. We can still see, though, that the surface of the reacting anhydrous grain is still quite rough. This roughness that emerged really quite early on is persisting because it seems we can have probably defects along certain crystallographic directions which make them more soluble than others. Of course, in this micrograph, we can also see that, of course, we've got the reaction of the alite. Here we've got the interstitial phases, the ferrite and the aluminate. Now, close to the surface, the aluminate has all disappeared, but here, where it's embedded in the ferrite, we can still see small regions of aluminate phases that haven't reacted yet. These aspects I brought together in this drawing I made quite some years ago now, which really summarized the microstructural development around 1 grain of cement. Another aspect which is important to talk about is to look at the different phases. So really we've very much emphasized the reactions of C3S and then of aluminate because these are the ones that react most. So in this graph here you see data from the literature for the 4 main phases. So we have alite here, we have aluminate here, belite here, and ferrite here. And then we have very similar data for 4 different cements which were studied in the PhD of Vanessa Kokoba. Now, what's very important is you can see that the alite is reacting most early on. That's to say, at 1 day, we have degrees of reaction between 40% and 70%. Really very, very high. And then that's increasing at, say, about 28 days to about 80%. And as we go on to 90, 100 days, it's approaching 100%. The aluminate reaction also very fast. You see we have high degrees of reaction at one day, again between 40 and 80%. And in this, in some cases, it's very quickly going up to 100% in just a few days. In other cases where it's more embedded in ferrite, for example, then it may take somewhat longer. So now we come to the other two phases we've hardly discussed at all, and we see in general the reaction of these two is much slower. Notably the B-light, and this is very important. I said several times before that it doesn't make any sense to produce high B-light cements because of the slow reactivity of the B-light. But we almost see that there really is this interaction between A-light and B-light. That's to say, while we have this fast reaction of A-light, as we see here, the reaction of B-light is hardly happening at all. So A-light reaction actually suppresses B-light reaction. And it's really only after 10 days and more that when the A-light has more or less all reacted, that the B-light reaction is starting to have any impact at all. Ferrite is a kind of intermediate case. In fact, we see that at one day the degrees of reaction may be quite high, about 40%. That's similar to the aluminate, but then it really slows down. And the reason for this is that this low solubility of iron in alkaline solution, so that after a bit of the ferrite phase has reacted, you kind of clog up the surface with, first of all, amorphous iron hydroxide, which really stops the rest of the phase reacting. That's just summarized here, that we have little reaction before 10 days, and that's actually thermodynamically controlled. Because of the reaction of the A-light phase, it suppresses the dissolution of the B-light phase. The aluminate is fast, but it can be slowed down by the presence of ferrite in grey cements. And the ferrite is slow, but it can quite be significant even at one day. Now, if we look at the reaction of these phases in the microstructure, B-light often gives us this very interesting pattern of reaction. We can see whether the certain striations have reacted while others have not reacted. And the reason for this is you get this, during the cooling of B-light, you get these multiple phase transformations which often occur by twinning, and then solutes tend to accumulate in some twins and not in others. And it's generally the parts which have the high solute content, which are more reactive and can react. So you see that the depth of reaction here is several microns, but then we've still got a kernel in the middle, which is unreacted. And this you can see even in very old cements. This micrograph here on the right comes from a piece of concrete that's about 30 years old. And you can see these large clinker grain. This was a cluster of B-light. This is quite typical in cements. You want to minimize these grains, but they do occur. And you see in this cluster of B-light that quite a bit of the B-light still hasn't reacted even after 30 years. Now, in that micrograph, this is like a zoom out of the one before. Now the only unreacted phases we see in this 30-year-old concrete are really B-light and, of course, the ferrite phase. This is the ferrite phase, these bright areas here. And if we look at this backscattered electron image, which is what was in the previous slide, it appears that the ferrite hasn't reacted. Even though when we go to the X-ray diffraction, this shows us that the ferrite phase has disappeared. And what happens is that the aluminate and calcium components kind of leach out. They disappear and form the normal hydrates, leaving this relic of ferritic silicious hydrogarnet. And this is what has been seen in quite old paste, well, even after a month or so, that the dominant phase from the ferrite is this silicious hydrogarnet. Now, coming back to the overall microstructure, we've shown this micrograph several times, And what I want to do here is to remind you that this hydrate phase that's between the grains, everything that isn't calcium hydroxide, is really a very fine mixture of CSH with ettringite or with AFM phases, monocarbonate, monosulfate, really mixed at this very fine scale below 1 micron. And we can see further evidence of this by looking at these microanalyses. If we make microanalysis and then we plot them on these graphs of alumina calcium versus silica to calcium, or sulfur to calcium versus alumina to calcium, we can see that what we have here, we have this cluster of points we see here and we see here, which is CSH, but the fact we get points extending along these lines is really showing us that we have mixtures either of calcium hydroxide with portlandite, with calcium hydroxide along this line, or with CSH with either ettringite or monosulfate. And we can see more clearly in this graph down here that we can differentiate much more easily between whether we have mixtures with ettringite or with monosulfate. So here, this is at 28 days. We see we've still got quite a lot of ettringite intermixed with the CSH, a little bit of monosulfate. And as we go on, first to 1 year and then to 3 years, we still see this very gradual shift as further ferrite probably reacts to now getting much more points along the monosulfate line. But we always see this persistence of this spread, this cluster of CSH points due to the intermixing. And, I want to emphasize that what we analyze here in the SEM, we're always analyzing a volume of 1 to 2 microns in dimension, which is why we see together these several different phases. So just to summarize this microstructure part, what we saw at the beginning was the same as what we saw in the reaction of the aluminate part, that the presence of sulfate modifies the reaction. We get a small initial reaction and then this long induction period. When the sulfate in solution is exhausted, we get this second burst of aluminate formation, and then finally the monosulfate or monocarbonate formation. And what we also saw in this module, we talked a little bit about Hadley grain formation, where we get these separated shells. We talked about the rates of reaction of the different phases and really emphasized that the B-light reaction is very slow, only significant after about 10 days because it's inhibited by A-light. We talked a bit about the ferrite. It seems to be unreacted. It's certainly not moved much. It stays in the same place. But in fact, it seems to react to form this poorly crystalline ferritic silicious hydrogarnet. And then at the end, we emphasize the fact that the aluminate phases, whether ettringite or AFM phases, are mainly finely dispersed within the CSH. So that's the last one in this series about hydration. I hope you've found something interesting and enjoy the rest of the course on characterization methods. Thank you very much.